So now we can look at the dissociation of water. So we said water is an amphoteric molecule, that it can act as either a base or an acid. And like all weak acids and all weak bases, water is going to be slightly dissociated into the proton and the hydroxide ions. And so we can say that there is some equilibrium that's set up in any amount of water where a little bit of the water is going to be in the hydronium ion state and a little bit of the water is going to be in the hydroxide ion state. So in pure water, the concentration of each of these guys is 1 times 10 to the minus 7 molar. So it's a very small concentration that is in the protonated and deprotonated state. So we can come up with an ion product constant then for water that will be given by this equation. So it's just the concentration of our hydronium ion times our hydroxide ion. And so we don't need to divide it by the total water concentration because that's going to be very, very high. So we know that in pure water, the concentration of each of these guys is 1 times 10 to the minus 7 molar. And so we can say that this times this then would be 1 times 10 to the minus 14 at 25 degrees Celsius. And so this becomes an equation that we can utilize for the water constant for the Kw. So we can define acidic solutions and basic solutions based on the concentration then of hydronium ions and hydroxide ions, because we know that the total has to come back to equal 1 times 10 to the minus 14. So if our hydronium ion concentration is increased and it's greater than 10 to the minus 7, that's going to affect the concentration of the hydroxide ions. That's going to make the hydroxide ions less so that this equation can still be true. So if this is greater than 10 to the minus 7, then this is going to have to be less than 10 to the minus 7, and they become out of balance from each other. If you have more protons present in the solution, this is our definition for an acidic solution. The solution becomes acidic in nature. And the higher the proton concentration, the stronger the acid in that solution. Our neutral solution is where the protons are going to equal the hydroxide ions. And so each of these is at about 1 times 10 to the minus 7 molarity. Based on this equation up here, that's going to be pH 7. Or neutral. If the hydronium ion concentration is much lower than the hydroxide concentration, this is when you're going to have a basic solution. So in this case, the hydroxide ions are increasing and it is a much greater molarity of the hydroxide ions than of the hydronium ions. So once we've defined our acidic, neutral, and basic solutions, we can actually use these concentrations of hydronium ions and hydroxide ions to indicate the strength of the acidic solution or the basic solution. But it's kind of inconvenient to use very, very small numbers, right? It's kind of inconvenient to use 10 to the minus 14th all the time or 10 to the minus 7th or the range that's in between those two. So instead of evaluating our acidic, neutral, and basic solutions based solely on the concentrations of our ions, we actually start to use a log scale, and this makes it easier for us to deal with the concentrations, and we can use the log scale that will give us a logarithmic range from 1 to 14 for us to gauge what the pH is. So the pH is essentially related to the log of our concentration of our proton ions, or the hydronium ions that are present in solution. So the pH is equal to the negative log of our hydronium ion concentration. The pOH is going to describe the basicity of the solution, and this would be minus the log of the hydroxide concentrations. So typically, we gauge the acidity and the basicity of the solution by looking at the pH. But you can do either. You can look at pOH as well. So we can go backwards from this equation. So if we have the concentration of hydronium ions, we can calculate the pH. Or if we have the pH, we can go backwards and we can calculate the concentration of hydronium ions that we have present. Same thing, if we then know how many hydronium ions we have present, we can use the equation from the last slide, this equation here, to calculate the concentration of the hydroxide ions that would be present as well. Similarly, if we know the concentration of hydroxide ions, we can calculate the pOH, or if we know the pOH, we can calculate the concentration of our hydroxide ions. Again, we can use this equation on this slide here to go back and calculate the concentration of hydronium ions if we know the concentration of our hydroxide ions. And we'll do some example problems to show how we can utilize all of these equations. I think that the biggest thing is learning how to use your calculator. So you need to take some time to actually practice doing the law calculations using your calculator, because it's very easy to make a mistake. You got to make sure that you've got the parentheses set up correctly so that you get the correct answer and you're not off by a logarithmic factor. So we'll do some practice. You'll do a lot of practice in the lab calculating pHs to get you set up doing this. And we'll do an example file with some sample problems of calculating pH. But essentially, an acidic solution is going to have a pH that is less than 7 and a pOH that's greater than 7. A neutral solution has a pH that equals 7. The pOH also equals 7. And our basic solutions are going to have a pH that's greater than 7, a pOH concentration that is less than 7. So just like we saw in the equation back here, our concentration of hydronium ions times the concentration of hydroxide ions is equal to 1 times 10 to the minus 14th. So it's a constant rate of dissociation. We can see that in our logarithmic scale that the pH plus the pOH has to equal 14 at 25 degrees Celsius as well. And so this is the logarithmic relationship of the equation that was on the previous page. So the main equations that you should be familiar with and remember is this equation here. This statement will always be true. Our proton concentration times our hydroxide concentration equals 1 times 10 to the minus 14. These two equations here are really important for calculating pH. pH is the minus log of our proton concentration, and our proton concentration equals 10 to the minus pH. So that's just altering the way we're looking at our log scale so that we can solve for either one of these depending upon what we know. We can calculate pH if we know the concentration of the hydronium ions, and we can calculate the concentration of hydronium ions if we know the pH. This is the other major important equation as well, that we know that the pH plus the pOH equals 14. So if you know the pH is 2, then you know the pOH is 12. And so it's very easy then to be able to use these equations to calculate the concentrations of the hydroxide ions or the hydronium ions, if you know one of these two numbers. This is just showing you how the concentration of the hydronium ions or the protons is related to the pH. So you can see it's going to be directly related to the pH. So as your molarity of protons is going to increase, it's getting much larger as you go down here, right? Because 10 to the minus 1 just moves the decimal place back 1. 10 to the minus 14 is going to move that decimal place back 14. So it's going to be 0.000000 all the way out to 14. Very small number, much larger big number. So our pH scale is just changing this logarithmic scale here to a single number system, so it's easier for us to work with and easier to look at. So our pH scale tends to go from 1 to 14, and it reflects the hydronium ion concentration or the concentration of our protons, which is indicating our acidity at very high concentrations of the protons. So our acidity is going to be low pH numbers. Higher concentrations of hydroxide ions is going to occur as we move up on our scale, and so the basic region of the pH scale is going to be above 7 and getting more basic as you go up in pH number. Remember, our neutral point is where the concentration of hydronium ions or protons equals the concentration of our hydroxide ions. and that occurs at this position here. Both are equal in their dissociation. So when you're working with pH, we just need to talk about significant figures as well. So essentially, your 10 to the minus pH, or you can take the anti-log depending upon what features your calculator has. So it's either going to be 10 to the minus on your calculator, or you can hit anti-log or inverse log. And then this would be the pH value. If the pH value has one position past the decimal point, when you write out the concentration then of your hydronium ions, you'll have a single digit. So the digits that you go out in the concentration reflect how far you go past that decimal. If you have two places past the decimal, this is going to indicate that you should have two numbers in your concentration of hydronium hydroxide ions. So if this is your concentration of hydronium ions, for example, 4.6 times 10 to the minus 3, when you calculate the pH, you take the log of that number. That would indicate that you should have two decimal places out from this digit because there's two significant figures in your molarity concentration.